And we are very happy to have Leeat Yariv here today with us. He is Ranger, Professor of Economics at Princeton University, and also Director of the Laboratory for Experiments in Social Sciences. Like more close enough. Okay. And before going to Princeton, she held faculty positions at Caltech and UCLA. I think I got that right. She has a PhD in economics from Harvard and previous degrees in mathematics and physics. She's an expert in experimental economics and theoretical economics, and very interested in collective decision making. That is about how we together make decisions, which is a great topic of conversation. Okay, so we're going to have the seminar until 5, and as always, after the seminar there will be a reception in the Dreyfus building, 6th floor. Okay, thank you. Please, let's welcome Leeat Yariv.
Thank you for the kind introduction. It's really wonderful to be here. So the motivation for this part of my work is that major decisions are often reached by a collective of individuals. So you can think about juries and courts, electorates and elections, boards and firms that decide on mergers, and so on and so forth. And in fact, you can even think about conflicts within oneself, where you're aggregating different motives within yourself, whether I should study for an exam or go to the movies and so on. This is in some sense like a group making a decision. Now, there's a rich literature of thinking how to design institutions to aggregate preferences and information, and that literature goes back to the 18th century. So one of my heroes, CONDORCET, came up with the first model for thinking about how to aggregate decisions. And in his model, he was thinking actually about the French Revolution at the time, and he suggested the following simplistic assumptions, where he said, well, suppose you have two states, so think about a jury, for instance, so we could think about a guilty or an innocent defendant, and there are common preferences, so everyone is trying to match their action with the true state. So for example, you want to acquit an innocent defendant and convict a guilty defendant. Each person receives some independent piece of information. So for instance, you might interpret different evidence during the court trial with your background in an independent manner, or you might read different sources of information when you were thinking about elections more generally. And the last component in what Condorcet was thinking about was sincerity. So he assumed that people would just vote according to the information they themselves collected. Now, all these assumptions led him to conclude that majority is actually a pretty good way to aggregate opinion. And in particular, it's superior to one dictator making decisions based on one piece of information. So basically, majority rule allows you to use more pieces of information than one dictator. And you can see how that ties to a situation where you're thinking about one king who's making a lot of decisions for a population. Now, there are many, many extensions in the over 200 years that followed. So one type of extension, follows under the rubric of social choice and asks, why should we think about majority? So May in 1952, in a very important result, illustrated some basic features of aggregation rules that would make majority uniquely desirable. Now, everything I'll tell you about today will entail two alternatives. With three or more alternatives, there's mess. And Condorcet realized that there are complications when there are three or more alternatives. Those of you who know about Condorcet cycles, this will ring a bell. Arrow's theorem is another manifestation of some of the basic problems that emerge when we think about three or more alternatives. With the emergence of game theory, people also started thinking about how voters might behave strategically. So there's a lot of work that started in the mid-1990s that thinks about strategic voters rather than these sincere voters who just mimic whatever information they received. Now, Condorcet thought a lot about aggregating information. Naturally, you could also think about aggregating preferences. So the literature has emerged to cover both of these cases, aggregating information and preferences. Most of this literature was theoretical in nature, but recently there are more and more experimental and empirical exercises. So what I'll tell you about today are a few pieces of evidence that we've been collecting and analyzing using both theory and experiments, which should raise the question of why should we even look at experiments. So let me quote again the Marquis de Condorcet, who said, "All phenomena are equally susceptible of being calculated, and all that is necessary to reduce the whole nature of laws to similar to those which Newton discovered with the aid of the calculus is to have a sufficient number of observations and a mathematics that is complex enough." So I interpret this as Condorcet encouraging us to run experiments. And nonetheless, there are many other reasons to run experiments beyond just listening to Condorcet. So this is an image of our new Princeton Experimental Laboratory for the Social Sciences that was opened last year. And here are some other reasons why we might want to think about doing experiments. So first of all, is that it's a highly controlled environment. So you can induce preferences, you can induce information in a way that we can't do in the field. We can also observe individuals interact multiple times with an institution. So for example, if you wanted to study an individual deciding in a presidential election, you would see them only every 4 years. And in fact, there would be many other things that would be changing about them as they proceed from one election to the next. We can also observe aspects that are very hard to gain from field data, like communication protocols that I'll soon tell you about today, or beliefs. We can easily track processes that take a long time to unravel in the real world. So suppose that I wanted to understand standard approving committees like the FDA. Their processes are very long. So if I wanted to study this, I would need to track them for a very long time. Last, we can try new policies fairly cheaply in the lab. So if you thought about, for instance, banning polls, you can certainly try to introduce that policy in the real world, but that would take a lot of effort. All right, so what I'll tell you about today is one aspect of group decision-making that I've been interested in, which is the impacts of deliberation. So there are many aspects of group decision-making that are interesting. I'm going to focus on this particular one. And the reason why I find it kind of exciting is because, in general, when you look at collective decision-making in the real world, there are two features that are common to almost every example you'll think of. The first one is that deliberation is common. So almost always when we make a decision with others, we talk beforehand, or we exchange some information beforehand. So you can think about jury deliberations, where this is part of, formally, of the process. You could think about hiring meetings for the faculty amongst you, and so on. The other item that's kind of natural is that there is a large variance in voting rules. In fact, even when you look at the same sort of decisions, there is a large variance in voting rules. So for example, if you look at civil courts in the US, even focusing on particular types of trials, you'll see a huge variance of the voting rules themselves that are being utilized. So the main questions that this work that I'll tell you about focuses on is how does communication affect outcomes, and what institutions are beneficial in the presence of communication. Now, the analysis is naturally extends to any application that pertains to collective decisions. I'll use a lot of lingo from juries, and this is just because the role of deliberation is very clear-cut and circumscribed for juries, so it's a very natural application. But everything I tell you would be relevant for any other small group of people that makes decisions. All right, so let me give you some just background data that has to do with the importance of communication. So this first piece of data is not from me. So this is Hannah Ford and a bunch of co-authors who surveyed jurors coming out of trials. So this is about 1,400 jurors from 170 trials. And they asked them, when did you make up your decision? At which point in the trial? And all I want you to get out of it is that the rightmost column that corresponds to jury deliberation is very high. So about 40% reported that they made their minds during the deliberations. Here's another piece of evidence from Hans, who surveyed 3,500 jurors from felony trials in the US. And what he looked at is the final verdict as a function of the initial leanings. So in the initial poll during the deliberation, he asked them whether they were strongly favoring the defendant being innocent. This is on the left, leaning towards innocent, and so on until strongly favoring guilty. And then he mapped the actual verdict. And what you see is kind of what you would expect from any sort of standard updating process, where you get information and you update, and naturally you see less updating, though some updating, at the extremes. All right, so this is what I'll do to you in what follows. I'll tell you about the most basic model of deliberative voting, and I'll show you some experimental insights on that. And then we'll go from those experimental insights and modify the model. And then we'll go back to the lab and test the new model. So that's basically the theme. Now, as a warning, I have only 42 minutes, so I will be fairly loose with details, and I apologize. If you want to know anything in addition to that, please talk with me in the reception or send me an email. All right, so in the first part, I'll be a little bit more formal, just so that we have the ground set for us, and then I'll become looser and looser. All right, so here is the underlying model, and this is originally a model that was done with my friend Dino Gerardi. So think about n jurors who need to select an alternative of acquit or convict, so A or C. Each juror has a type, TJ, which is private information, which is private. So this can stand for some information, what they read or how they grew up. It could stand for preferences, whatever you want. The set of types is then just this vector of types of individuals. The probability distribution will be denoted by P here. It can entail correlation or not. And a juror's utility is a mapping that takes us from the final decision, acquit or convict, the set of types, and maps it to the real numbers, like usual. So why is the dependence on the entire profile of types? Because in the case of information, I might actually care about information that other people have. Okay, so this allows us to think both about the aggregation of information and of preferences. Now, jurors' J's actions are just to vote for acquit or convict. And the set of all voting profiles is this capital V. Make sense? All right. So under voting rule R, alternative C, or convict, is selected if and only if there at least are votes cast in favor of R. So for example, if you thought about R, which is half the population, this is basically simple majority. And if R equals to N, that's unanimity for conviction. Okay? So this is the threshold of votes. How many votes do you need in order to get conviction? All right, so there's a lot of analysis of these sorts of games, and in general, behavior and outcomes depend on the voting rule. This shouldn't come as a shock. Now, what's the important thing to notice when you have strategic behavior? In a strategic game as such, voters contemplate information in the event that they are pivotal. So they only think about cases in which they are pivotal. The mere fact that you're pivotal tells you something about what others have chosen, potentially what others' types are. So under majority, for instance, you're pivotal if precisely half the population voted acquit and half the population voted convict. In unanimity, you're pivotal if everyone else voted to convict. So naturally, these events might entail very different information, and that's why you'll see different behaviors and different outcomes. Now let's think about adding communications. So suppose the jurors can communicate before they cast their votes. Now I'm being loose here on what I mean by communication, but think about any situation where you exchange some messages between you during the deliberation. Now, formally, for those of you who know cheap talk games, I'll just mention it in 2 bullet points here. We're essentially looking at a cheap talk extension of the game defined by each voting rule. So essentially, what we're interested in are the set of communication equilibrium outcomes in the sense of Meyerson 1982. But informally, just think about any situation where you learn something about yourself, you talk with others, and ultimately you get some gut feeling as to how you should act, acquit or convict. Now, what does the proposition tell us? When we look at equilibrium outcomes here, equilibrium outcomes are going to be mappings from the entire vector of types. So this is all the details of the information and the preferences of individuals in our electorate or jury, and the final outcome, the probability that they choose to convict and the probability that they choose to acquit. When we allow people to talk with one another, these set of outcomes don't depend on the voting rule. One exception is unanimous voting rules. So these actually lead to subsets. This is a theoretical subtlety. You'll soon see where it's coming from. But in general, if you look at non-unanimous voting rules, they shouldn't matter for outcomes. So I'm now going to give you a brief heuristic intuition for where this is coming from. This will be the only sketch of proof that I'll show you today. So I hope you can bear with me. All right, so what do we mean by a communication equilibrium? So this is a very cynical view of thinking about how we talk with one another. But essentially, we come into the conversation with our types, our information or preferences. Then we talk with one another. I'm going to put this in the square, whatever messages we send to one another, whatever we tell one another. And ultimately, we leave the communication, and we have some conviction as to how we think we should vote. So this conviction might even be probabilistic. Maybe I leave the jury deliberation, or we end deliberations, and I think I'm so confused, I'm just going to toss a coin. I'm going to choose something random. Or not. So with each of these probabilities, there is a vector of actions that each person decides to vote. And this vector of actions, acquit or convict, is going to map to a final choice using the voting rule. Okay? Now, one of the classical results in economic theory is what we call the revelation principle. Now I'm going to do a caricature of the revelation principle. What does it say? It says, well, suppose you started with an equilibrium with this complicated game in the top where people talk with one another. We'll bring in a mediator who emulates precisely what happened in the deliberation room. So they'll just mimic whatever people were saying to one another. So now people will reveal to the mediator their types. The mediator will emulate whatever happened in the communication room and just spits out the recommendations that would have emerged anyway if you let them talk by themselves in this equilibrium. So this is we're just exchanging the communication with this mediator who is a black box who knows how the communication should proceed. Why is this useful? It's useful because now we essentially need to worry only about 2 things. One, we need to make sure that people are willing to tell the truth to the mediator. And the other is that we need to make sure that when the mediator dispels this recommendation of what to do, people actually are willing to follow their recommendation. So as it turns out, the strength of the revelation principle is that you can always do this with any equilibrium. So in some sense, if you think about the set of communication equilibria, you can focus on equilibria of this sort, where you tell something to the mediator, and the mediator then gives recommendations to everyone.
How do you handle the impact that the deliberation tells each juror how the other jurors are telegraphing how they're going to vote?
So right now, I'm kind of this is completely a mechanical thing. It's an abstract theoretical construct, and each person is only told what they should vote. Now, I think what you're asking, which is a very good question, is how do we implement this in real life? And in real life, in the room, we actually talk with one another, and we see messages. Some of the messages are public, maybe some are not. Can we circumvent the existence of the mediator? And that's a very deep question. And there are some results that show us that we can do this if we have enough people playing the game. So in particular, as it turns out, if you have 5 or more for sure, and for most games 4, we know that you can do this. You don't need the mediator. But I won't get into this. These are very deep theoretical questions. All right, so what's the trick? So now the trick is the following. So before, the mediator gave the same recommendations that the people would have out of the communication. So now let's assume that the mediator, instead of giving these various recommendations, she gives only unanimous recommendations. So whenever a vector of recommendations here, a profile of recommendations led to acquittal, she will tell everyone to acquit. And whenever a profile led to conviction, she will tell everyone to convict. So now let's think about incentives here. So in terms of truthfully revealing to the mediator, this alteration doesn't change anything about the distribution of outcomes, right? The distribution on acquittal or conviction are exactly the same as they were before. So this shouldn't affect the willingness to truthfully reveal. Now, how about following the recommendation? Well, as long as the rule is not unanimous, you can't affect the decision now because you're never pivotal, right? If you have simple majority, for instance, and everyone is voting to acquit, you changing your action is not going to affect the outcome, right? So now this thing is essentially independent of the voting rule, and you see where unanimity is kind of different because we would need to have an extra restriction that assures us that people want to follow the recommendation. Now, what is it in words? What does it mean? What it means is basically we sit in the room, no matter what the voting rule is, let's decide what we want to actually implement. So if you think about a faculty meeting trying to hire someone, we can discuss what we want to do, and ultimately just decide unanimously. Let's just decide what we want to do, and we can circumvent the voting rule by voting in consensus. That's basically what's going on here. All right, so let's, the next step is looking at experiments that see if this sort of result would hold water. So the experiments were done with Jakob Hori, and what we did is a 3x3x2 design. So we varied voting rules. We also varied preferences, although I won't talk about it today. And then we allowed people to talk or not in the lab. So these experiments were run in the California Social Science Experimental Lab at UCLA. May it rest in peace. It's no longer in existence, with about 550 participants. Each treatment was 15 rounds with a practice round, so people got to interact with the interface. They were randomly assigned to groups of 9 people, so that's the group for us. And they had to guess one of 2 equally likely states, red or blue. And I'll soon show you images of the interface so you'll get to see what participants saw. Now, there are 3 voting rules we wanted to compare. Simple majority, so where the threshold was 5, you needed at least 5 people to choose red or convict in order to get red as the group choice. 2/3 supermajority, where R equals to 7, so where you needed at least 7 people to choose red in order for the group guess to be red, and unanimity, or R equals to 9. All right, now in terms of payoffs, we did various types of payoffs, but what I'll tell you about right now are what we call homogeneous payoffs. So that's basically a setting like the one we started out with, where all you want to do is match the group decision to the actual jar that had been selected. So again, 2 jars A and B. If the group guess matches the actual jar, everyone gets 100 points here, which translated to $1. If the group choice doesn't match the true jar that had been selected, everyone gets 10 cents or 10 points. All right, so this is what it looked like. We had 2 jars. So we had a red jar. This is jar 1 on the left, which had 7 red balls and 3 blue balls, and jar 2 on the right, which had 3 red balls and 7 blue balls. And at the beginning, we selected one jar, and we showed them a jar with the balls hidden. And we told them that we were shuffling the jar. Okay, so they knew that the location of the balls might be different than the previous picture. And they could click on one of these balls. So without communication, once they clicked on the ball, they could choose the guess, jar 1 or jar 2. When communication was allowed, once they clicked on the ball, a pop-up screen showed up, and they can communicate freely with one another. All right, and once they were done, everything was revealed to them. They could see the actual jar that was selected and their payoff and what others did, everything. All right, so here are some statistics that we saw. So first of all, when we look at the messages, almost all of them are truthful, and very few actually, no one lies, and very few say nothing, although some say nothing. And most of these messages are public, so they're sent to everyone. There's no reason for them really to create coalitions in this case. Now, in terms of outcomes, that's the main result that I just showed you theoretically. If we look at the probability of convicting, or the probability of guessing red for across the different voting rules, as a function of the number of red signals in the group. Okay, so this is really the object that we're interested in. Here, every person receives a signal, and we want to understand what's the probability that we get to choose red, or convict, say, given the information that's available to them, the number of red signals in the group. Now, what you see is what we might expect from the original models of strategic voting, or any game that would be played here, which is that the voting rule really matters a lot. So in fact, when we have unanimity, it's very hard for them to get agreement on everyone convicting. However, once we allow them to communicate, we get almost identical outcomes. So what you see is that this kind of echoes what I showed you theoretically, where there is very little difference between the voting rules. Now, in terms of what underlies this, of course, there's a lot of analysis that one could do here, but just to give you a glimpse of what happens here, what I'm showing you here are the number of people who are voting for the ultimate guess. So for example, when they chose the red jar, a 5 majority means that precisely 5 people chose the red jar, and 6 people chose, and 4 people chose the blue jar, and so on till unanimity. So what we see here is that the majority of cases, the modal case, is a 5 majority, where 5 people choose one way and 4 people choose another. When we go to communication, we see exactly the reverse. The modal outcome here is a consensual selection of the guess. Right? So this is precisely in line with this intuition that we can circumvent the voting rule by voting in unison. Let me give you a sense of the messages, as this will feed into the next step. So here's one protocol of communication from one treatment, just to give you a sense of how it looked. So red, red, blue, 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 red, blue. Position is different on every screen. Upper right, blue. Jar 2, everyone please say again the color once only now, thanks. Blue, red, blue, blue, blue. Jar 2, majority equals to blue. 6 blue. Jar 2, yes, blue, please, for everyone. All right, now what you notice from this thing roughly is that initially they're sharing their information, and then they're coming up with an aggregation. So in fact, we had a few research assistants who classified different messages into what we called signal revelation, where they just reveal their own signal, into what we called positive comments, which are comments about how we should act. And what we saw here is we normalized every protocol of conversation. And what we saw is essentially what I just showed you in this particular protocol, where in the first part of the communication protocols, they tend to share their information. And in the second part of the protocol, they tend to share what they think should be done. And this is true for pretty much every treatment we have here. So this is for voting rule number 5. This is for 2/3 majority. And this is for unanimity. So they basically look the same. So this is an interim summary. What we see is the following. So without communication, we have strategic voting. And we see a lot of difference between the voting rules. With communications, we see very similar outcomes across institutions. So at first glance, it seems as if the institution almost doesn't matter here once we allow people to talk. And communication protocols are public, they're truthful, and they seem to have these two phases where they first reveal information and then they decide on what to do. And everything I told you about here assumes homogeneous preferences, so everyone shares the same preferences. And while this is kind of the common assumption in this literature, this is you would think that this is exactly the case where it would be very easy to communicate because we all share the same preferences. Why wouldn't we share our information? As it turns out, we see actually very similar effects even when preferences are different in the population. All right. So looking at this set of communication equilibrium equilibrium outcomes, kind of this theoretical exercise that I started with, we saw that the predictions across all these communication protocols, if we looked at the set of predictions across any possible protocol, we would gather that these sets are the same across institutions. That was the first theoretical result I started with. But now we see a particular protocol emerging in the experiments. So if we focus on a particular protocol, then maybe institutions would actually start playing a role. So we wanted to try to understand what are the impacts of very particular protocols that seem to mimic something that looks real, either from the field or through the lens of our experiments. So in fact, many protocols are designed this way. So if you think about jury deliberation, a lot of it is about recalling and analyzing evidence publicly in the jury room, and then deciding what to do later. But also, if you think about standard-setting committees like the FDA or the EPA, they perform a sequence of tests prior to making a decision. And they need to decide when to stop making these tests, just like a jury needs to decide when to stop deliberating and make a choice. So the new goal in the revised models, this is work that was done with Jimmy Chen, Alessandro Lizzeri, and Wing Swan, was to think of deliberation as information acquisition and ignore everything else about deliberation. So basically, we'll just think about deliberation as this process of information revelation or acquisition and then usage of this information. So, yes?
Is affect part of your definition of information?
It could be in the original result, because these types, I'm very agnostic about what they stand for. So they could be what you call affect, they could be preferences, they could be information, what have you.
I actually meant in terms of intensity. I believe this passionately versus I believe this.
Yes.
Are you
yes.
adjust for that?
Yes. So you could do that.
See that in the
yes.
vector that you set up.
Right. So in principle, these utilities are arbitrary functions of the types. So it might be that particular people respond differently to their types.
I meant in terms of the way it was projected.
In the experiment?
Yes.
I see. So in the experiment, the type of heterogeneity that we dealt with was not maybe quite what you have in mind, but rather what we thought of is some people liking more a particular state. So some people are red partisans, for example, where they really want the red to be selected.
Right.
So in that sense, we did that in the lab.
And you can mark that how they were partisans?
We just paid them more when Red got elected. Yes, yes. And we saw very similar results. It would be a bit more convoluted to show you, so I'm not going to show it to you today. All right, so the modeling approach goes back to the father of sequential sampling, Abraham Wald. And interestingly, from a historical perspective, as it turns out, the idea for sequential sampling originated from other people. So this is a quote from Abraham Wald in 1945, who said, in March 1943, the problem of sequential analysis arose in the statistical research group Columbia University in connection with a specific question posed by Captain Schuler of the Bureau of Ordnance Navy Department. It was pointed out by Milton Friedman and Alan Wallace that the mere notion of sequential analysis could slightly improve the efficiency of some current most powerful tests. So I never thought of Milton Friedman as the true father of sequential sampling, but there you go. So what we're going to think about is a collective action version of Wald's sequential sampling. And for those of you who are not familiar with sequential sampling, I'll explain it in a minute. So for now, I'm going to give you a sketch of the new model. I'm going to do this in discrete time just for simplicity's sake, but then we'll shift to continuous time versions when I tell you about the experiments if I have time. All right, so here's the new model. So it's going to be very similar in some features to the original model we started out with. So you have a state of nature, whether the defendant is innocent or guilty, and they're equally likely. And there's a committee of end jurors who need to decide whether to acquit or convict. And each agent now is characterized by a preference parameter QI. So this preference parameter basically tells us how painful it is for the juror to convict an innocent person. And -1 minus QI is how painful it is to acquit a guilty person. And acquitting an innocent or convicting the guilty, we normalize it to having no cost. Okay? So basically, the skew captures the ratio between type 1 and type 2 error. I always make type 3 error, which is confusing type 1 and type 2 errors. All right, so what is deliberation? So at each date, all agents have to decide whether to continue deliberating or stop deliberating. Okay? So this will be the process. So there are going to be two rules that govern this, and this mimics these two phases that we saw in the original experiment. A deliberation rule, it's going to be a threshold voting rule. This is just like the threshold we saw before. And if at least RD, or this is the R deliberation, choose to stop, deliberation stops. So if enough people decide that they want to stop and make a decision, the deliberation stops. And otherwise, you continue collecting information. Deliberation is costly, so sitting in this room is costly if you forgo wages, for instance, or it's just painful to sit and chat all day. And when deliberation stops, agents are going to vote. How is voting done? Voting is done in much the same way it was done before. So again, we have now a decision rule, which is also this threshold voting rule, which captures how many people you need to convict in order to convict the defendant, okay? Just as before. Now, how does the information go? Agents observe a realization of a sequence of random variables. So at every period, they get some piece of information that's conditionally independent, and it costs this fixed amount of money. Now, for those of you who are more entrenched in these models, we'll assume that these signals are symmetric for now, but let me not go into the details. All right, so how do we interpret this new information, this model? Well, you could think about this new information in various ways. So for example, if you think about hiring committees, we first read people's papers, then we invite them to campus to see them, then we might call them up again, and so on and so forth. So this is kind of a sequential process of information collection. In the jury, similarly, you can think about every day as deciding whether we're done with deliberating or should we continue for another day. So this is a reduced form model for more information that emerges from more communication. All right, so for homogeneous committees, this is not due to us. This is a result that Wald solved himself. And instead of, given the time, let me not go into the formality, I'll just show it to you in a picture. What did Wald say? Wald said, the solution is very intuitive. Once you get sufficiently convinced that the defendant is guilty, you should stop and convict. Once you get sufficiently convinced that the defendant is innocent, you should stop and acquit, and in between, you should continue collecting information. So the real magic is identifying these thresholds, but in general, what will characterize your decision are two thresholds. So what you see here is information that evolves over time, and at some point, if the probability of a guilty defendant is sufficiently low, you choose to convict. And if the probability that the defendant is sufficiently high, you choose to, you choose to convict. Okay? So there are these two thresholds. So what we were interested in heterogeneity of this group, and there are various results that emerge. So I'll skip the cost heterogeneity, but let me tell you something about preference heterogeneity. So suppose that we have a symmetric jury with homogeneous cost here. What we could say is that deliberation length and accuracy of decisions increase with deliberation and voting rules. So now you can actually affect the decision of the jury by changing the voting rules. And in fact, there are many results that come out of this sort of way of modeling things. So I don't have time to give you details, but let me tell you some things that emerge from this. So first of all, in terms of delegation, we know that all jurors in a symmetric jury will prefer majority rule. So this gives you a sense that majority rule may have another reason for existing, because everyone in the jury, at least, prefers to have it. There is a limited voting irrelevance, and two items that are kind of, I think, easy to interpret are, first of all, as long as the deliberation rule is more stringent than the voting rule, we should have a voting rule invariance. Why is that? Because you agree to stop communicating when you're sufficiently convinced of one thing relative to the other. You're so convinced that the voting rule, at the voting rule stage, you're for sure going to get whatever decision you held during the deliberation stage. The other option is that the costs are very low. In that case, you collect so much information that you become sufficiently convinced once the voting rule, once you come to the voting, and you know what you're going to vote for, and everyone agrees on what should be voted on. There are also other kind of counterintuitive results that these models generate. For example, they tell us that when you have heterogeneity both on the cost and the preferences, then you might have people who are very impatient having a lot of power on how the decision is made. So it might be that just because you have one person who's really impatient, everyone is drawn to a very hasty decision. And all of us who've sat on committees know what I'm talking about. All right, so in the last few minutes, I'll tell you a few words on some experiments that look at this. So these are new experiments with some of the same set of authors and a stellar student at Princeton, Paloom Rashidi. So what we do is essentially consider the sequential sampling and classical hypothesis testing in the lab. So what is classical hypothesis testing? For those of you who do econometrics, that's your bread and butter. So essentially, it's a problem where we're trying to assess how much information should I collect to make a decision when each piece of information is costly. But this is done statically. So we'll look at sequential and the static decisions amongst individuals and groups. And for groups, we'll look at majority and unanimity. So the main questions that we're asking is, do individuals and groups actually follow what the theoretical predictions may suggest? Do groups behave differently than individuals? And do institutions matter? So in this sort of processes, would we suddenly expect to see majority and unanimity at least differ in the outcomes that they generate? And just kind of foreshadow what I'll show you in the next few minutes, what we first see is excessive information collection in classical hypothesis testing. So when they choose the amount of information statically, they choose too much information. We see time decreasing thresholds in sequential sampling. So what I just showed you from Wald was that you should have these fixed thresholds over time that govern your decision. What we see in the lab is that people actually have declining thresholds. Groups behave differently than individuals, and we see the least information collection under majority in dynamic setting, and sequential sampling is actually superior to static sampling, which is what we would expect. All right, so let me tell you how the experiment was designed. So this is, I'll drop the theory parts, but essentially it's a continuous time variant of the model I just told you about. So we have two jars, jar A and jar B, just as before. And they're equally likely at the outset. And the task is, again, to guess which jar had been selected. The group gets $2 if they guess correctly and $0 otherwise. And the information now follows a continuous time random walk. So the only difference is that it has drift mu if the jar is jar A and drift minus mu if the jar is jar B. And the same variance. Yeah?
How did you communicate that to the subjects?
That took a while. We actually approximated a discrete time random walk, and we diminished the time differences. So I can show you slides later. Yeah, that took a lot. It's not trivial to explain this to subjects, so we gave lots of examples. We constructed it in the lab, yeah. So wait, no, we didn't. So just so that I complete that, there is a fixed cost of information here, which is 40 cents. And in order to avoid, to circumvent any issues with Bayesian updating, this is a complicated problem. It would be, it's even for me, I need to take a piece of paper to calculate the optimal solution here and to figure out the posteriors. So we weren't really interested in seeing whether they can do Bayes' rule. So we explained the whole process to them for the sake of transparency. But ultimately, we just showed them directly posteriors. So essentially, they saw the scale that had the probability of jar A and the probability of jar B. There was this little dot that moved around as the probability as you progressed in time. So they learned more and more. And this dot, after a long time, naturally moved to the ends of the scale. Now, as long as a decision has not been made for individuals, they received additional information, so they could see the dot continuing to move. And at any point in time, they had to decide whether to stop and guess A, stop and guess B, or wait and choose W. This is waiting and collect more information. And the threshold that corresponds to this theoretically is 0.80. So once the probability hits around 80%, they should stop. The feedback is that they saw the correctness of the guess and the payoff. So they saw basically everything that could be seen at every round. For groups, we had groups of 3 that were randomly rematched each round. And at any point in time, each member made a publicly observed choice to stop and guess A, stop and guess B, or wait and choose W. And once a majority or unanimity decided to stop, the information collection stopped, and the guess was whatever corresponded to the majority or unanimity. So in order to isolate sampling behavior from preference aggregation, here we're focusing on homogeneous groups. So everyone has the same preferences. So in some sense, you would expect, theoretically, to get exactly the same results as individuals. So there's no real difference. The feedback, again, is everything that happened in the game. So this is what the interface looked like. They had the dot. They could see exactly what other people in their group were choosing, and they could choose between A, B, or W. And once they chose, they saw everything that happens. Let me skip the static. So just as a summary, this was run at the Princeton Experimental Laboratory for the Social Sciences. Each participant experienced only one of these treatments. They were run for 30 rounds plus 2 practice rounds, and they were paid for 20 random rounds. And at the end of the experiments, we also elicited risk attitudes and altruism from them in case these matter for how they behave. Yeah?
If I may suggest a variable to consider, why not put, just to deal with the point you made 90 seconds ago, why not put a Bayesian calculator in the interface and see if they use it?
That's not quite the question we're after. I have 3 minutes, so let me get back to that so that people can be released and I'll be done. So I'll just show you kind of the main results, and then I'll be done and people can go. All right, so I'll just show you kind of the main thing from the dynamic and give you a teaser for the static. So what I'm showing you here are the cumulative probabilities of different posteriors upon decisions. So this is what is the posterior, once a decision has been made, what is the posterior? Now recall that theoretically, they should all stop when they hit a probability of 80%, either for jar A or for jar B. So if they were all, bless you, voting according to the theory, we should just see a spike at 81% and nothing anywhere else. Now, of course, it's no one would expect all participants to exactly nail the equilibrium. So what we see here is a distribution. What's interesting is that majority is taking the least time. They're the fastest when they're making decisions in the majority. They're the slowest when they're making decisions in unanimity. So you might tell me, well, this is just a mechanical effect. You're drawing 3 people from a distribution. So obviously, we're going to see, some differences. We should expect that. So let me just try to convince you that this is not the case. So what we did here is essentially take our subjects that chose individually and randomly simulate groups of 3 people from these data. And then say, what would we expect to see were they making choices using majority and using unanimity? And what you see is these dashed lines. And in particular, we would expect majority to make decisions much more slowly, or to choose posteriors that are significantly higher than what we see in the lab. So in other words, there is some effect of majority that we're seeing here that goes beyond just a mechanical effect of grouping people together. For unanimity, it looks very similar to these mechanical effects. All right, so we're out of time, so let me give you parting thoughts. So theory and experiments shed light on processes that happen in groups. There are many other aspects of collective action that I think are really exciting. So one is that standard preference aggregation may actually lead to seeming biases. So for example, groups that aggregate discount factors, even when they're strictly exponential, completely standard textbook discounters, when they make decisions in groups like a household, they suddenly become what we call time inconsistent. Suddenly they have these wacky discounting functions. And this is inherent to group decision making. It's very hard to avoid that. The other thing, once you think about it this way, is how do we think about elections when the people who are voting for you are actually subject to these biases? So now with all this emergence of nudge policies, are they good? Do they enable these biases because it's the voters who are biased who are voting on these policies that are aimed at quote unquote fixing them, or can they actually backfire and actually make things worse? So these are some kind of exciting things to follow up. Thank you very much.